Yeah, welcome to our presentation about nnInteractive. First of all, before I start, I really want to mention that this was a huge team effort within our department. I mean, we are the first authors here, but as you can see, the list is long and going on. And we also continue to work on this project. And it has been a really, really great journey. But I guess everything was kind of started with Meta's SAM model, which is basically a model for very simple interactive prompting. So you click on an image and the respective structure you click on is being segmented. You can do this multiple clicks. And the idea is that you can basically segment anything. And this is exactly how the paper was then in the end called. And of course, it didn't take long that we had medical adaptations for those for this specific idea. After the SAM and SAM2 paper, there was very quickly from Yun Ma a paper called Segment Anything in Medical Images. And it didn't stay at that. There's actually a plethora of other medical adaptations. We have various different venues here. We have MITK NeurIPS with Zegwal, Scribble Prompt at ECCV, Vista at CVPR, so you name it. Very high ranking and very cool as in the first view, cool segmentation papers. But then this kind of begs the question, is the problem solved? Are we actually at the point yet where we don't have to, we can like focus or divert our research into another direction because this has been solved? And this is exactly where we started off, where we thought we'd try out the tools that they have provided us. And we started off with an online demo of the NVIDIA tool. So it's the NVIDIA Vista 3D tool. And as you can see here, if you just click on the kidney, you kind of get an insufficient result. And then you repeat this with multiple clicks and it doesn't really get better. And same goes for Zegwal, which is a NeurIPS spotlight paper even. And you can see that you get a very chunky segmentation of the liver in the very right picture. And then you place another point to make it a bit better, and it doesn't really catch the point. And now you could say this is kind of cherry picked, but actually this is on their own online tool with their own images. So basically if you look into this a bit deeper, then you see that it doesn't really make sense to just use your own images, but it also already breaks at images they provide. And yeah, we show this again here, basically, that if you just look at the online tool, you can see it doesn't really matter. Also, liver is a very like simple segmentation target, and it still doesn't really work. So we moved this a bit further from this quantitative analysis to actual quantitative analysis and wrote a quick paper about this, basically benchmarking all of the models out there, including the SAM and SAM2 model. I'm gonna spare you with the details. It's basically at the time that we found out that SAM2 is still outperforming many of those plenty medical adaptations in the 3D and 2D space. And each model kind of has their own sweet spot, what it's designed for. But there's no really a model out there which really does it well, all of it well. And with that, we just found out that there's many different research gaps in all of the different models, and I'm just going to very quickly brush over them. First of all, if you have a 3D volume which you are interested in, the 2D models don't work. For example, here you see the slices just break down. I mean, each slice is having a different segmentation, and it's not contiguous at all. And if you then basically move on and look into the open setness of the models, then you quickly find out that the models are designed for specific segmentation targets. I mean, this is a GitHub page where you want to download a specific model for colon, pancreas, or liver cancer, which in the end is, of course, something you could just train a unit on. Why would you need an interactive segmentation model for that if the model only works for liver cancer, for example? And many of them also are modality specific, so CT only, or even dataset specific. Then next up, right, we want to be user friendly. I mean, I mentioned this tooling we used earlier. These are online tools. None of the methods before have actually provided tools integrated in any commonly used viewer, and the online tools are very slow. So we didn't want to work with that as well. This is also an angle of attack. And last but not least, most methods are not truly interactive. And this is about interactive segmentation. And truly interactive is by us kind of defined that if you place a first prompt and it doesn't work, or the segmentation is almost perfect, but not really perfect, you want to be interactive. So you have the ability to place another prompt. And the first model, which I presented, basically the Metzer model, wasn't interactive at all. You could just place boxes, and this model here, which is called SAM 3D, also just has the ability of point prompts. And with all that in mind, we basically set out to build nnInteractive.
Exactly, and this is where I take over now. I hope I got the slide transitions somewhat right, Max. At least you didn't have to remind me, but it's always challenging to do that for somebody else. Yeah, so nnInteractive. We've heard about all the shortcomings of existing methods, and now we really wanted to do this right, and we felt like there was a huge opening in the field to address many of these issues. So let's rehash, or let's introduce nnInteractive in terms of what we wanted to achieve. What is it we want to do? And first of all, we want nnInteractive to be able to work with a diverse set of possible prompting styles. This is different to the models that we've previously seen, who only either allow points or maybe a bounding box, and then point refinement is like the most complex thing that exists out there. One method, scribble prompt, does scribbles, but then it only really does scribbles and only in 2D. So here we really want to allow everything, and we do not only want to allow positive prompts, but we also want to be able to allow the user to say this thing should be removed from the segmentation, which is also something not all existing methods support. We want this to be native 3D, so no 2D slicing, and also all the segmentations that are being generated need to be generated in 3D. And we want these interactions to live on 2D planes in the 3D image, because we feel that this is something that's really needed to ensure usability. So the human interacts with these 3D images through the screen, through a 2D plane. So expecting them to set a 3D bounding box is a very complicated endeavor that is very difficult to implement in a way that it becomes user-friendly. So all our interactions need to be 2D. So a 2D bounding box generates a 3D segmentation, or a 2D scribble in one plane generates a 3D segmentation. And we want to be able to generate these 2D interactions in any plane of the image, so that you can always orient the image in a way such that you have the optimal view of the object you're interested in. And finally, we of course want this to be open set and modality agnostic. So open set means we want to be able to segment any target structure that we see in the image. And we also want to be able to do that in any type of 3D image without having to have seen this modality previously during training. So say we want to be able to do this now on some certain microscopy images, even though we've only trained on other types of images in the training set. So what we really want this to look like in the end, and just to introduce the setting a little bit, is that we have some image with the target structure, which is just outlined here in yellow for you guys to see what it is we're currently interested in. And we want to set a certain prompt, in this case here, just a point prompt in the object. And in an ideal world, we already get like the perfect prediction by nnInteractive, which is then the final result. But of course, we don't live in a real world, and as good as a tool you're making, you're always not going to be perfect the first try. So we definitely want the tool to be able to consider corrections by the user. So in this case here, we're starting with the 2D bounding box. And this 2D bounding box, you're seeing it as a 2D plane in this 3D rendering of the segmentation. So it really is a 2D interaction. And then the user can do refinement of the initial prediction. So in this case here, there was like a small thing missing. So the user now adds a point prompt, because the user deems this the correct prompting type at this point. And then the final prediction is what we're interested in. As I mentioned, we want this to be as dynamic and flexible as possible. So what we are showing here in the two examples further down is not only are we changing the prompting style between the initial prediction and the refinement. So here we start with what we call a lasso prompt, and we are then switching to a negative scribble to remove something that was over segmented. But we are also rotating the viewpoint between the different interactions. So we start in one slice, and then we're switching to a different like view orientation because we are seeing the error better in that view orientation. And all of that we want to be supported. And finally, what you're seeing here with this knee example is like an out of distribution example that's supposed to highlight the open setness and modality agnosticity. Yeah, so, and I think with nnInteractive, we've actually managed to achieve all of these things. Please excuse the low resolution of the video. I'm fixing that right now. So here you see me interacting with nnInteractive in the Napari imaging viewer, and you're seeing also me make corrections. So here you see there was something missing in the segmentation, and it really nicely responds to additional prompts. And you see me use like all these different prompting styles in different orderings and like with different in different ways. And what you're seeing here as well is me segmenting first the liver, and then in a dedicated segmentation layer, I was segmenting the tumor. And this really highlights that we also want to be able to resolve ambiguities. So what is it that the user wants? Do they want the liver? Do they want the tumor? We really want the tool like build nnInteractive to follow the user's guidelines here. Yeah. So let me play this out for a couple more seconds. In the end, we see a 3D rendering of the segmented objects, and this really shows you that we have now successfully created a bunch of 3D objects with very simple interactions in this image. Yeah, so how does nnInteractive work? Conceptually, really, it's very simple, but as is often the case, the devil kind of lies in the details. So in terms of how we are approaching the segmentation, one thing we noticed with all the existing methods is that they relied on a bunch of different segmentation architectures, but none of them really considered what's actually considered state-of-the-art in the medical domain. And surprising as it is, even though this was initially released, like, I don't know, 2019 for the first time, and then UNet is still the most relevant segmentation method today. It's being downloaded like crazy, and also in all the conferences at the competitions, we see people using it, adapting it, and really using it as a starting point for state-of-the-art networks. So this is also what we want to base nnInteractive on, and it's surprising to us that nobody has really done that so far from the competing methods. So yeah, but the UNet is just that, right? It's a segmentation architecture that can generate segmentations. How do we now interact with the UNet, or how do we build a method around the UNet that allows us to achieve all this user interaction at test time? So the first thing we need to do is we need to be able to encode the prompts somehow. And here really we chose the simplest way possible you can do this, which is that we just inject additional input channels into the UNet alongside the image. So there's nothing fancy going on here. It just takes 8 input channels as opposed to 1 input channel, which would be what a canonical, like fully automatic UNet would do in this context. And the input channels we're choosing here is, of course, the original image that has the imaging information. We are injecting a previous mask channel, which allows like the whole system to remember what the previous prediction was. And then we have 6 interaction channels where we have 2 channels for each interaction type, a positive and a negative channel, and we are separating the interaction channels by interaction or prompting styles. So we have a set for points, a set for scribbles, and one set that is shared between bounding box and lasso interactions. So the UNet sees at the very least the image plus 1 initial prompt that indicates the object that is to be segmented. It will produce a prediction based on that. It will consider the interaction to guide what object is to be predicted. And during the training of nnInteractive, this prediction is then compared with the ground truth. And what we then do is we iteratively let the UNet refine its own predictions during training. So during training, we need to simulate users that further interact with the segmentation. And we're doing this in a way where we have like certain user profiles, so users that, for example, switch interactions randomly between refinement steps, or users that pick one interaction and stick to it throughout the whole refinement process. This is just to simulate a little bit the human behavior. And then depending on what kind of user type we selected, we called those interaction agents, we can decide like what should the next interaction be. So given the previous prediction and the previous interaction, do we now then again, in this case here, we again say, let's pick a lasso and make it a positive interaction and let the user try to add something that was missing from the previous iteration. And this is basically on a high level what the training looks like. So we basically just show these examples and we rotate them a couple of times through this loop so that the UNet really can learn from its past mistakes and correct them with the help of user guidance. We trained nnInteractive on a really large data set or collection of data sets, rather comprising 120 publicly available data sets. In total, we have like over 60,000 annotated volumes with many more individual objects in them. So that already alone allows for a very robust method that can work with many target objects. But we also extended this data set of human labels with a large number of pseudo labels that we automatically generated. And I just want to dive into that quite briefly, because this is also another vehicle that allows us to further improve robustness and generalization to new objects. And what we did here is basically hitchhike off of SAM2's success. So one of the big things that SAM introduced was consistency across slices. So that in SAM2, this is done for videos, but we can also extend this concept to 3D images. And here, Max really put in a lot of effort configuring and heuristically selecting or discarding automatically generated labels by SAM2. And as you're seeing here with the ribs, the segmentations aren't perfect, and this is fine. This is intentional, because what we're doing by these imperfect segmentations is that we are essentially contradicting other labels that we have in our data set, so that we force the network to figure out what it is that the user wants, rather than just relying on predefined concepts like the rib classes we already have in the training data set. So now we have an interactive trained. Let's benchmark it. I just want to give a short overview here of the benchmarking data sets that we used, and we separate our benchmarking in two different categories. The upper data sets here are data sets that are more or less near OOD. So we didn't train on these data sets, but the modalities and or objects that are inside these images are similar or are known from the training data distribution. So this is a setting where we're applying an interactive on known concepts, but on new data. And then the far OOD setting at the bottom is basically new modalities and or completely new structures or like new organisms. So what you're seeing here is, for example, we have mouse data with mice that have tumors, and we've never seen mice before. So how do we generalize to that? We're looking at insect brains, also something we have never seen, and some other things that are completely new to the method. Yeah, so and this is our benchmarking data set. This is what we conduct experiments on also for the competing methods. So let's look at the results. This slide shows results for a single interaction. So no really interactivity, just a single prompt and the result to see like what's the initial performance of the different methods. And this also allows us to really nicely compare with a large number of methods, because not all of them support refinement. So what we are seeing in nnInteractive is the red column, and of course it performs the best across different prompting styles. I should also emphasize that when we are doing point prompts, all the 2D models perform quite well here, but this is just because for the 2D models we have to give one prompt per slice, whereas for the 3D models we give one prompt period. So the 2D models are actually require a lot more effort to get to this state than the 3D models. When we look at interactive performance, so how does the model react to user input? We can only do this with points, unfortunately, because none of the competing methods allow refinement with boxes or any of the other prompting styles. But when we focus on points and do that, we see nnInteractive starts strong and continues to dominate the pack. So there's no competing method overtaking nnInteractive's performance. Here again, number of points means number of points per slice for 2D models, which gives them a strong advantage. And the 3D models, which is ZegWall, nnInteractive, and I believe SemMed3D, they only receive really the number of points that's given on the x-axis. This result is particularly encouraging when we compare the performance of the different prompting styles. So what you're seeing here on the right is just nnInteractive, but nnInteractive comparing the different prompting styles with each other. And we see that points, which was the best among like all the methods that support any form of interaction, is actually the weakest interaction type with nnInteractive. We see that the lasso prompt, which I will show a bit more in the next slide, really is very strong, starts strong, finishes strong. And we see that other interaction types like scribbles, which are also very fast to do, we like using them a lot. Doesn't start as strong as some of the others, but really finishes strong. So we see there's a lot more to be like more performance to be had if we move away from just point interactions. A short detour on why lasso is so effective in this context, maybe a short definition of what we consider a lasso interaction. So what we say, so what we are seeing here is the target structure. This is a kidney in a CT image, and a bounding box prompt would look kind of like this. The issue with the bounding box is it's very coarse. It's not clear what does the user want really, and usually this requires then further interactions to resolve any kind of ambiguities, like do we want these vessels here to be included or not? So in this case here, we would have to set like a negative point or something like that to remove them. With lasso, what we're doing here is we're just encircling the object of interest we want. This encircling doesn't need to be precise. It's only on one slice, and you just like wing it with your mouse somehow. It's very forgiving, is what I'm trying to say, but it contains a lot more information than just a bounding box. And with that information, we can resolve many ambiguities, and this is why the lasso interaction starts out so strong from the get-go. So really, this is the strongest initial interaction to do. In this case here, it's displayed as a polygon, but really the lasso interaction is just a 2D binary image that we give the model. So it doesn't need to be a polygon, it can also be a 2D segmentation slice or something like that. So far, all the benchmarks have been done using simulated interactions, which is just out of necessity. There's like no way to do this consistently with humans. But there are some data sets out there that contain human annotations, and one of them is MSCMR is, I believe, the name of this data set, which comes with human-generated scribbles. And we also use that in our benchmark to verify that the effects we're seeing are not only related to the way we're simulating the prompts, but also holds true when we use the human-generated prompts. And here we see that nnInteractive keeps its lead relative to a scribble prompt, which is like the only other method that allows scribbles to be used. And it even keeps that if we reduce the scribbles to only 3 slices, whereas scribble prompt always has to have scribbles on all slices because it's a 2D method. We also conducted a small human reader study with clinical partners who used nnInteractive to annotate various lung tumors and other structures. And they found that even though they were like completely new to nnInteractive, they didn't have any meaningful prior training, they were able to save like about 72% of annotation time. And I would only expect this number to go up if the users were like comfortable using nnInteractive and have used it already for several hours. Here's an overview of a few qualitative results. You're seeing one example from our far OD distribution here, which is the mouse data set, and then some of the others. And what you're seeing here basically is a repeat of what Max was showing at the beginning. So we have the 2D models sometimes struggling with consistency across slices, and then we have some generalization issues and some fallback maybe to known structures. I don't exactly know what was going on here, but we see nnInteractive in these cases performed quite nicely. Yeah, with that, I'm already basically at the end of the presentation. I just wanted to show some more wild examples that we worked on for demonstration purposes. So these are 4 examples that are not necessarily known to nnInteractive from its training distribution, except maybe the microscopy example. But you see here like a a bird claw, frog organs, or fish. And in all of these different images, even though we've never seen this species before, we can work with nnInteractive to segment target structures and to get what we want. Let me continue. Yeah, so nnInteractive has been included in several user-friendly tools. The list is incomplete, I must confess. There have been some more in the meantime. You can find them on the nnInteractive GitHub repository. But I think the most well-known ones are covered here, which is Napari, MITK, 3D Slicer, and ITK Snap. So nnInteractive is available for you to use in any of these tools in a way that is user-friendly and fast. There is some differences in the implementation side. If you're starting out, I would recommend you try MITK or Napari, because these were the ones we were directly influencing. The others were built by the community and may deviate in the implementation for how we did it ourselves. And then also it depends a little bit on your setup. So nnInteractive really needs a local GPU, because CPU is way too slow. So the Napari and MITK versions work locally, whereas the 3D Slicer and ITK Snap variants have like a server client setup that would allow you to connect to a remote GPU and then work with that. So they are a little bit more involved when you're setting things up. But if that's what you need, then this is like if you need the remote GPU, then 3D Slicer or ITK Snap are probably the way to go. Yeah, with that, we're at the end already. Thank you so much for your attention, and we're really looking forward to your questions, and then also to the images you may or may not have uploaded in the meantime. I see an image, which is cool. So yeah, let's first start with questions, and one comment maybe. The image that was uploaded is a CZI image, which I'm not sure we will be able to open. We can try, but if you have it in a different file format, like a TIFF image or something else, that would be awesome to have as well. All right. I'm using the Napari plugin here, just because that's what I'm most familiar with. But in principle, you could just as well use use MITK or any of the others. You see a question. So you provide a 2D segmentation. How do you guarantee the consistency for the 3D prediction? So the consistency is really something the network figures out in the prediction process. So the reason we include the prompts at the very beginning as input channels is in order to allow the network to guide the feature extraction and prediction process from the very beginning with the given prompt. And the network is able to expand that basically in 3 dimensions and select the correct objects and boundaries based off of that. I don't have a much better response to give you, rather than simply due to the way we trained the network, expecting it to give 3D outputs from 2D inputs, and due to the way we constructed it, as opposed to many of the existing methods which do late prompt injection. This is just something that works, and it produces very nicely consistent 3D results. No complaints from our users so far regarding that. Okay.
All the training of the model were done on medical images. You did not use any images of fluorescent images of cells or.
We do have some non-medical images, but unfortunately, the internet is much sparser, much less densely populated with non-medical images than it is with medical images. So we tried to figure out, and we wanted to include as many microscopy images as possible. And we do have some. We have some cells. We have some other structures, but we really had issues finding training data. So if you have any training data that you could share, we would be very happy to include it in the next iteration of our training.
Basically anything that is interesting to you and that is kind of publicly available and has 3D segmentations. It doesn't really matter what modality it is. Could be anything, microscopy, or medical related. The model should just learn to adapt to a natural 3D setting.
Nicolas, you had a question?
Yes, thank you for this very interesting and clear presentation. Is there a size limit in the image size you encounter during your training? Because medical images are less big than light sheet microscopy or other kind of big data. So do you have some limit yet, or no, it's not just a patch size and batch size, and then it's done?
And nnInteractive always works on the patch size that is used during training, which is 192 cubic. We do work around larger objects by having like an automatic zoom out functionality that will perform a zoom out on the image such that the target object fits the patch. But the issue is that this has its limits. So for very large images, nnInteractive and also all the current implementations you see will not perform properly. I would say like a reasonable upper image size is something like 800 to 1,000 cubic. Anything beyond that, it would be necessary to do some pre-processing to the image. So you either downscale it if the object of interest is large enough, or you need to crop an area of interest from that in order to plug it into nnInteractive.
Okay, thank you.
So I see another question in the chat. What was the next? So what we're seeing here is just a CT image. We have not trained on this image. It's part of some test set. But again, just to show you that things work and also things work quickly, which is important for usability. This CT image, I'm not sure if I can get the dimensions here, but it should be 512 by 266 in terms of image size. So yeah, in principle, we can do like a scribble annotation. We get an initial prediction. This is an error that occurs quite often here at the liver for some reason, but we can easily fix it. Also, what's hard to see is that here is it's a vessel in here, located here. Let me see if I can enhance it a little bit. So you see there's like a vessel here, which is currently being included partially. We can also tell nnInteractive to exclude it, which it will then happily do. We can also tell nnInteractive to exclude the tumor from the liver. At least it should do it. Now it's fighting me. It's always like that when you do presentations, right? It doesn't work. It never works as expected, but it's supposed to exclude the tumor from the liver. Let's just ignore that for now.
In the beginning, you put the scribble on top of the tumor.
That's a very valid point. Thank you for highlighting that. So that's a user error on my part. But in order to not drag this out too long, let's just continue. So we also can easily do something like a stomach, which is a very annoying structure to segment because it has like this high intensity region, which is basically water and then air in it usually as well. It doesn't get the borders perfectly, but you can just force it to follow the borders unless you, of course, are like me and create contradicting predictions. So here, just to demonstrate also, we can like mix and match interactions. I'm adding this part with a lasso. So yeah, and of course we can do this in any plane. So I can start with a point on the vertebra here and then move back to the axial view. And if I find any mistakes, I can do adjustments here. Like there's a small point missing, so I can add another point and it's gonna include that. Romain, you seem to have a question. Let's start with that, and then I look at the chat again.
Hey, thank you. I'm sorry, it's not directly related to the presentation, but seeing you scrolling in the Z made me wonder, did you try to use it for tracking instead of segmenting objects in 3D? Like if you have, for example, a cell moving in on a 2D plane across time, is that something you have tested?
So you can definitely just interpret that as a 3D image and try segmenting it as a 3D object. That should work. But okay. I think Max also has some special things to say about tracking.
Well, this is kind of like tracking in 2D, what you were mentioning. So stacking basically every image on top of each other. this should work as long as the movement is not so stark that you don't have any overlap between frames, because if you don't have overlap between frames, it might break, right? And also, I'd say just from experience, and we're working on that as well, nnInteractive is not working perfectly for long tubular structures. So everything which is like thin and long breaks at some point. But we're aware of that and we're working on that. But for tracking in 3D, basically, that's also what I'm partially interested in my PhD. There's also another method out there where we get basically interested in tumor tracking, but then we have 3D volumes and then subsequent 3D volumes. So in this case, it's actually 4D tracking. And there we use a registration-based approach that we basically register the prompt to the next step and then segment again, but we use information from the previous scan. If you're interested, the paper is called lesion locator. But as I said, that's kind of a yeah. I can add it to the chat. But this is, as I said, 4D tracking then.
Yeah, great. Thanks.
Another question in the chat. On what computer are you currently running RAM and GPU, so we can know what it requires in terms of resources?
Yes, so the computer I'm currently running this on is quite beefy. So it has a modern 8-core CPU. It has 64 gigabytes of RAM and an RTX 4090 GPU. But this is not the specs you would need to run nnInteractive yourself. So for running it yourself, like any regular CPU with, let's say, 32 gigabytes of RAM and GPU with 8 to 11 gigabytes of VRAM should be fine for most use cases. Ideally, you want a GPU with like more than 12 to be on the safe side. But it doesn't need to be anything expensive, like just a regular consumer GPU. It needs to be NVIDIA because of CUDA and entrenched ecosystems, but like any like gaming GPU like RTX 5080 or something like that is going to be totally fine. We have, Romain, before we continue with you, we have some more questions from the chat that I'd like to quickly get to. Also regarding anisotropic images. So one typical thing you do as a part of preprocessing in the medical domain is to resample all images to a common voxel spacing, and this would potentially cause problems when you're really going for open setness and cross domain. So we do not do any resampling of images in nnInteractive. The whole thing operates on the original image as it is, like in its native voxel grid. So it also works with anisotropic images. But of course, then as soon as you get very thick slices and objects move a lot between slices at some part, it starts to break down. But in principle, there are no issues with anisotropic images, also because we see this a lot in the training data set, that we have, say, an in-plane resolution of 1 millimeter, but then out of plane is 5 millimeters. So like something like a 5:1 ratio is something we have seen in training and we should be able to deal with. Then there's a question by Arthur. So we added 7 channels to the UNet, most of them binary images. Could you optimize it, put all binary masks into one int32 channel, ? So what I didn't explain here is that we don't just put binary images into the UNet, but we actually all of these images are floating point, and we are using some sort of decay, like intensity decay between interactions, also simulated interactions, so that the network can a little bit see what's the history of prompts, like what is the recent prompts, what was the one before that, what was the one at the very beginning. And we're doing that in order to inform the network better what prompt it should prioritize. So it's not necessarily integer. And even if it was integer, I don't think it would be good to stack this all into one channel for a convnet, because the convnet just interprets intensities and then would be really difficult to discern what's the like newest interaction or what type of interaction am I even seeing. Like if you put the bounding, like the scribbles and point prompts in the same channel, the network wouldn't be able to develop dedicated processing paths for the different interactions to optimally use them. Roma.
Yeah, sorry. It was about the hardware and installation procedure because I tried ITK Snap and the installation was very smooth. It's very great. Kudos for that. I think the one that is very automated is CPU only, though, for me, because it's with venv and I think things were not set properly. But just to mention that on our wiki, maybe I will add the link in the chat. We detailed how to use it with a member, Conda member environment and how to install. Also, we had an issue with GPU 5090, which is with a new architecture. And just to mention that to everyone, it's fairly easy and it goes very well.
Since we had this issue again this morning in an internal meeting, there is a problem with Torch 2.9.0, and it's imperative that you install something smaller than that. Okay. Because there was a cuDNN bug which caused the Torch developers to disable cuDNN paths, which causes performance and VRAM issues. So make sure you're installing Torch 2.8. something or previous versions and not 2.9. And depending on what operating system you're on, the default Torch installation will or will not support GPU. So when you go to the PyTorch is the only dependency that we recommend you install manually before you install nnInteractive. So you go to the PyTorch website and click on Get Started, and then we don't want that. So you need the previous versions of PyTorch thing. And then for like 2.8.0 or something like that, you need to make sure that you're picking one of the CUDA versions to be installed and not the CPU-only version. So if you're on Linux, the CUDA version you want is the one... When you run the NVIDIA SMI command, the CUDA version that you want needs to be smaller than the CUDA version that's reported by your GPU driver. If you want to be on the safe side, you can just pick the smallest one. It doesn't make a difference really. So you install PyTorch manually, and then you follow the rest of the standard Python installation, and that should get you the desired result. Awesome. We have one more question by Sheng Yang. Great talk, fan of nnUnit. Just want to know more related to nnInteractive. When generating pseudo labels using supervoxels, nnInteractive relied on high confidence masks produced by SAM. However, because these high confidence regions are usually the ones the model already performs well on, continued training on them may provide limited new information. If this and could potentially lead to could this potentially lead to diminished performance? So we use these SAM2 generated masks just a small fraction of the time during training. Most of the masks we used were the human generated ones, and then these SAM masks were used, I believe, 10 or 20% of the time. And they were just there. They were, like, as I mentioned before, intentionally imperfect, so that the model would have to figure out from the prompts what it is that is the correct ground truth here. And this could then, for a given structure, either be a human label or the SAM label. And we think this helped. This really helped with generalizability to new objects, because we're not just falling back to known task categories all the time. All right. Do we have more questions? If not, I would attempt to move on to the image that was submitted. I will also refresh again to see if we have more images in the meantime. No, we don't. Okay, so this is the image that was submitted. It's quite out of distribution, so let's see how we are performing. Starting with my favorite, the scribbles, and making some corrections. So yeah, seems like we are kind of picking up the right object, but of course it's not perfect, so we can try to do some more refinement here. So at the top here, there seems to be a part missing. And please excuse me if I'm annotating something wrong. I'm not familiar with interpreting.
You do it very correctly. Do not worry. And awesome. It's impressive.
Awesome. Yeah, it's you see a bit of a limitation here, which is that it's something we are currently addressing. It's always like the last couple slices that, for some reason, we sometimes have holes in that are difficult to get rid of. So this is a known issue, but we're working on that. Yeah. So I think we're doing an okay job here. It's of course debatable if we want to include that part here or not. But yeah, seems to work. Success, zero-shot generalization. Cool to see. Thanks for sharing the image. Awesome. Maybe something to show you as well, because of the speed with which we are generating results. I can also show you something here in that regard. So yeah, when I have loaded now a new image and we have a console output, and you're just seeing in terms of the turnaround times for the prediction for single objects is quite fast. Of course, that's now on my system, which is a little bit overpowered for what we are doing. Yeah, but really, as long as we stay in the small object, in the small object size, we have quite fast predictions. But if we do something where we need to trigger the zoom out, so you're seeing here that we did a zoom out by a factor 1.5, and then we had to do some more refinement. Then at some point it starts taking a bit longer. And usually in these CT images, the stress test is the liver, which still remains under a second, but then now we have multiple bounding boxes that we had to do refinement on. Romain, in question.
Yeah, sorry again. Do you send the entire image all the time, or do you compute it once and after you refine with this? I'm sorry, I didn't get. Maybe you mentioned it.
So what I'm referring to here is the automatic zoom out procedure. That I can demonstrate that, I think, quite nicely. Let me see. So when I disable the auto zoom functionality, we always only predict. Okay, bad example. let me restart.
Rather use point prompts for that. I guess.
So here you see it. With the auto, we always only send a patch of 192 cubic centered around the current interaction to the network. And what we sometimes see is that the object we're interested in exceeds this patch that is visible to the network. And we have built an outer loop, so to speak, for that to detect when we are touching the borders. And if we do, we are zooming out until we are no longer touching the borders with the predictions. And once that is completed, we have a coarse segmentation of the target structure. And this coarse segmentation, we are then refining again at full resolution with nnInteractive. So if I create a new object, I enable auto zoom again, and I try to repeat this scribble that we did before. You see that we triggered this auto zoom functionality. So it says we start with a factor of 1, then we zoom out again until we see the entire object. And then we do a refinement with a couple of bounding boxes on the zoomed out object to capture it in its entirety. This works up until an auto zoom factor of 4. The more you auto zoom out, the more VRAM and RAM you need. So this is why we are limiting this to a factor of 4. But it helps us deal with these large objects.
Okay, thanks. And is that working the same with ITK Snap? Because it was quite a bit slower on our machine, which is also quite well equipped hardware-wise. And I'm very impressed with the Napari version you are showing now. It's very fast.
I can also show the MITK version. It's equally as fast. If something deviates from that, then unfortunately this is beyond our control, because we only implemented MITK and Napari. So this is the same image. I need to create a segmentation. This is a leftover of our testing this morning. Okay, I can initialize nnInteractive, which I hopefully is not the broken version from this morning. So we do lots of internal testing, but it seems to work. And here again, see. So this is now the text output of MITK. It also prints the same thing. And if I now do a scribble annotation for the vertebra, it should also give me. So initial segmentations are typically slow, but when I now do the next label, we're also again back down to those 130 to 150 milliseconds turnaround times. It just calls the same backend in nnInteractive. And we can also, workflow's a bit different here, but again, do the same with the liver, right? We get the whole liver again. And here also we take which is basically the same as we had before. So this is what we had before, and this is what we have here in MITK. So yeah, I think it's if it's substantially slower, then I would relate that to the server client setup that this tool uses. And it's a community contribution. We're extremely grateful for that. People did it without us asking them to do it. So it's awesome that it exists, but we of course didn't influence that in detail.
Okay. No, thank you again.
Okay, 3 minutes to upload. So somebody is, it seems, trying to upload another image. Unfortunately, this folder that I shared is also sometimes a bit finicky. But if it doesn't work in time for the image upload, feel free to just test nnInteractive yourself. I think the installation is easy enough. Romain also seems to have already something working that he can share. So yeah, I can only encourage you to give it a try and to give us feedback in case something isn't working as expected. Please, again, send us annotated data if you have some. We would really like to only include data that's publicly available because we don't want people to say we are only good because we train on private data. So if you have something that we should be aware of, let us know.